What? He did not go back in time to kiss his mom. That just doesn't make sense.
Well, I can help you understand. Who are you?
Well, I'm you from the future. Hey, do you know how time travel works? Alright. So the question is time travel possible? Hi, my name's Aaron, and join me as we explore this expansive question. As far as the answer to this question goes, relatively speaking, yes, time travel is possible. In fact, people are doing it every single day of their lives. But it might not be what you may be thinking. Now, when I say speaking relatively, I am of course referring to Einstein's theory of general relativity. This theory suggests that time is relative to speed. Meaning, the way you experience time is relative to how fast you are moving. The only constant in this theory would be the speed of light, which occurs at a speed of 3 times 10 to the 8th meters per second. Pretend this is a mirror, and pretend this is a lantern. The speed at which the light bounces off the lantern into the mirror is the same as when it's moving. But of course, when it is moving, it occurs in a more irregular pattern, more of a diagonal, if you will. This is because at a stationary point, the light bounces from the lantern to the mirror consistently, but as our train begins to move with the lantern and mirror on top of it, the light keeps up with the train, but also consistently bounces back from the lantern to the mirror, so it creates a shape like a wave. Now I know what you're thinking. Okay, cool, but how does this relate to time travel? Well, that brings me to the next piece of scientific jargon, which is time dilation. It is the slowing down of a clock as determined by an observer who is in relative motion to that clock. The idea of time dilation says that either observers can say that something or a set of events happens simultaneously, but the other will disagree, seeing as their time occurs differently for them. But really, neither of them are wrong. They're both correct. Now we move into the actual mathematical view of time dilation, where t equals the time observed from the moving object, v is the velocity in which the moving object moves, c is obviously the speed of light, and to is the resting frame time. Let's say you are standing on Earth for about 10 years, 10 years goes by, and there's a spaceship flying in space going at about 28,000 kilometers per hour. So if we take that number and put it in terms of the speed of light, which turns out to be 9.3 repeating times 10 to the negative fifth, and plug it into the full equation, as so, we will turn out with a number that is 9.999999956. How about a more extreme example? Imagine you're going 0.95 times the speed of light. You plug it into the equation, and you come out with 3.122 years instead of 10. As the math shows, the faster you go, or the closer to the speed of light you get in your moving vessel, the slower time will move for you. I should also mention, for our connection to calculus class, that the equation we use for determining the time dilation between two objects, one stationary and one not, is actually a derivative of this equation that we use to figure the time it takes for light to bounce from the lantern to the mirror, or in any general case, the light source to a mirror while it is moving. Except the work for such a derivation is not quite as simple as I say it is. In regards to everyday life, every time that you increase your speed, whether it be getting on a bicycle, or getting in your car, or getting on the train, you are time traveling because you're experiencing time different from everybody else who is stationary. The increment of time in which you are experiencing this difference or this dilation is so incredibly small that it would be almost nearly impossible to actually recognize the change. You are still traveling forward in time. So we know how to travel forward in time, but what about backwards? This is where the science of time travel gets very mucky and confusing. In fact, a lot of scientists believe that traveling back in time is just not possible. Now, luckily for us, there are a few theories that we can take into consideration instead of just saying that it's not possible. Theories suggest that since going closer to the speed of light will slow down time, if you go faster than the speed of light, you would essentially reverse time. This theory is flawed because, as Einstein's equations show, an object at the speed of light would both have infinite mass, yet a length of 0. Which, trying to draw that, is quite the abomination. Another theory suggests that scientists should open 2 wormholes at different points in time. The problem with this, though, is that, for one, scientists now don't have the technology to actually build 2 stable wormholes, and if they could, scientists theorize that they can only send very small particles. There are also a couple of other theories that are not as far-fetched, like the theory that you could create a closed time-like curve using the Tipler cylinder, which is an infinitely long cylinder that has a very large amount of mass that bends space-time and creates a time-dragging effect. A lot of big words. But since the Tipler cylinder has such a large mass, it warps space-time. So essentially the theory goes that if you take a spaceship or a vessel of any kind and flew around the Tipler cylinder enough, you would essentially come out on the other side before the time that you entered. Another theory suggests these theoretical cracks or defects in the universe as a result from the Big Bang, which are called cosmic strings. They supposedly have so much mass that they would bend space-time drastically and might make time travel possible. Theory also has some problems because it's a major issue trying to find these cosmic strings, because for one, we have no actual proof of them existing, other than a few calculations that show. To say the least, harnessing one would be quite difficult. All of these theories have the one thing in common, that is warping space-time with a large amount of mass and energy. Another idea is to fly around the orbit of a black hole. This would try to replicate that effect of speeding up towards the speed of light. But in order to do this effectively, you would also have to be close to the speed of light. That, and we don't want to talk about what happens when the human body goes into a black hole. So, as you can see, when it comes to time travel, it's not that simple. Going forward in time, it's all about speeding up. Going backwards, you'd be meddling with forces beyond our comprehension. Now, if you'll excuse me, I have to go murder my grandfather.